name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. What I want to talk about in particular today are the operator selectable detection algorithms that the spectrum analyzer is able to implement. So just briefly as a recap, first of all today will be spectrum analyzer detection algorithms. We'll briefly recap the way that the spectrum analyzer works. I'll start with an analog spectrum analyzer. First, there's an input. Coming out of the input, we go into a variable RF attenuator, and this allows us to adjust the dynamic range of the spectrum analyzer's response. We'll talk about that more at a later date. Then, typically, in most spectrum analyzers, you either go through a 3 gigahertz low-pass filter, if you're looking at signals below 3 gigahertz, or through some kind of a tunable yttrium iron garnet YIG filter for higher frequencies. And then you may or may not have a choice on whether you're able to pass directly through what amounts to a straight line versus whether you have an option to go through a low noise amplifier. We will make use of the low noise amplifier today. And again, we'll talk more about the low noise amplifier at a later date. But typically you've got these as operator selectable choices. And then there are a series of down conversion stages, just mixers. And how many stages you go through depends upon what frequency you're going to tune the spectrum analyzer to. And remember that every time you go through one of these steps in mixing and down conversion, you'll see some kind of increase in the noise floor on the spectrum analyzer's display. Frequency versus power on the spectrum analyzer. And you'll see these little stair steps. And these stair steps, you'll recall, are typically on the order of 5 dB each for the stair steps. And you turn it on. Then, coming out of the last down conversion stage, you're now at intermediate frequencies, IF, and at this point there is usually a tap out provided, which is an IF output that you can use for auxiliary purposes. This will come out of the back of the box somewhere. Other than that, the signal flow goes through some kind of selectable IF filter, and this is often but not always called a resolution bandwidth. And then there is a log stage, a log amp. Then there is an envelope detector, which I draw like a diode. And then there is a selectable low-pass filter, which is a called a video filtering. We'll talk about that some today because that has to do with the detection algorithms. And then finally, there is a detection stage, a detector stage, and then finally the output. Just as I was about to run out of space. And so to make it clear, the function of these different stages is this adjusts dynamic range, this adjusts pre-selection, so that you can tend to reject signals that are not on the frequency where you're trying to do a measurement. Then this stage adjusts sensitivity. Then this stage down converts. And then this is the stage that determines the convolution function through which we'll observe the spectrum. This stage gives us a log function, which means that we now convert power into decibels. This stage provides envelope detection. Which means that this is the point where we lose the phase information in the waveform. We lose the phase information at that point, right there. No more phase information. And then finally, low-pass filtering, which has the effect of smoothing that waveform envelope. And then finally, we come to what I want to talk about today, which is the so-called detection algorithm. And the detection algorithm determines what we're going to pull out of the waveform. And by the way, if we're looking at this as a digital spectrum analyzer, the only difference between the analog and the digital is that in the digital spectrum analyzer, there is a filter here which is 2.56 times the width of that bandwidth, and then this functionality in a digital spectrum analyzer is subsumed in an application-specific integrated circuit, an ASIC chip. One other thing that I need to mention very briefly is that at this output in the analog spectrum analyzer, there is an analog to digital converter circuit. And in the digital spectrum analyzer, the analog to digital converter circuit is located right in here. So it goes in the digital spectrum analyzer, it goes digital, then it goes into the ASIC chip. So but the functionality is the same in every case. So, with that said, what happens after the signal's been processed through all these stages, and basically the signal's gotten to the point where, in effect, we're going to select what we're going to show on the spectrum analyzer screen from the waveform that's been flowing through here. Well, the way that spectrum analyzers are designed and built is that there is a display which, of course, can be viewed with the eye or can be, in effect, output through a digital bus at the back of the spectrum analyzer. And the display usually is set up to show frequency versus power. And we'll also look at the ways that we can make this show time, show power as a function of time. And so we get some kind of display running across here that shows something like this. But in fact, what's going on is these points on this trace are discrete, like so, working their way across. And I call these bins. So we have a set of bins across here. And each bin represents an output from the analog to digital converter. In the analog analyzer, the ADC is located after the detector. In the digital analyzer, the analog to digital converter is up here, but the final output is still binned. It's still going to show as a set of bins. And the bins are discrete points where a discrete power level is shown as a function of the bin number. And the problem that we have when we're operating the spectrum analyzer is to decide, in effect, on some waveform that's coming into the spectrum analyzer, what information we're going to put out on the screen or into the digital output at the back of the analyzer on a bin-by-bin basis. so. And so I'm going to draw a set of bins across here. And I'm going to magnify these bins such that they'll look like this. And so forth across. And so this will be my bin number 1, bin number 2, bin number 3, number 4, number 5, and so on across. By the way, the typical number of bins that you'll find in a spectrum analyzer display may run anywhere from a low value of about 601 to a high value of about 8,192. In some spectrum analyzers, that number of bins is hardwired in. In other spectrum analyzers, you can select how many bins you want to display. So here are the bins, just 5 of the bins out of those large number of bins on the spectrum analyzer display. And here is the waveform which is coming through these bins like so. And the problem is, what do we want to show on the spectrum analyzer display on a bin by bin basis? So down here is the display, the output, if you will, that we're going to show. Well, one detection algorithm that we can use is an algorithm which essentially locks to the highest value that the waveform achieves on a bin by bin basis, like that, right across there. And this is positive peak detection, like so. So positive peak detection always picks off the highest point. Now, in an analog spectrum analyzer, there's actually an analog circuit that actually latches up to the highest value that occurs on a bin by bin basis. And at the end of each bin cycle in an analog analyzer, that latch is reset, and then the latch traps again on a high point on the next bin. The value's taken out, then it's reset, and then it latches and so forth across. In a digital spectrum analyzer, of course, it's fairly easy to run the equivalent of a kind of a maximum level sorting routine and just retain the max level. But in both cases, you get this. And so what we would display in the spectrum analyzer, in this case, would be a level that would look like that, and then a level that would be a little lower like that, and then a level that would be almost the same like that, and a level just a little bit lower here, and then maybe a level just a bit lower than that. And this is what you'd actually be displaying on the spectrum analyzer if this thing were running with a positive peak detection selected. The next one is so-called negative peak detection. And as Paul McKinnis pointed out to me, it really shouldn't be called negative peak detection. It really ought to just be a minimum detection. And in this algorithm, we always pick off the lowest value that occurred anywhere in the bin. And let's see, on this one the lowest value is right there. And on this one the lowest value is right here. On this one the lowest value is right there. And so if we were running this spectrum analyzer with so-called negative peak detection, that's what we'd be bringing back for each of the bins. So we'd plot a level that would look like, I'll adjust my own dynamic range here like so, like that, like that, like that, and then that, and something like that. So that would be negative peak. Another detection algorithm that we can pick is so-called sample, or sample mode sample detection. In sample mode, a point is pulled off arbitrarily inside each bin, and I'm going to say that the point is pulled off as the very last sample point in each bin. It could be the first point, it could be the last point, it could be the middle point, it doesn't matter. It's just the same point relative to where the waveform is running in the bin on each bin cycle. So, so let's see, we get here and here and here, and then finally we'd wind up in this one right there. So sample pulls off a point arbitrarily out of the input waveform, and you can consider it to be a random sampling unless there's some behavior of the waveform relative to the speed that this thing is running through the bins that makes it somehow synchronous between the waveform and the way that the bins are being sampled. So that is sample. And notice that sample values could go anywhere from positive peak levels to negative peak levels, or anywhere in between. It just depends on what happened at that moment at the end of the bin. So here we would have something like that, and then on the next bin the sample would be right down there like that, and then on the next bin just a little bit higher, whoop, like so, and on the next bin a little bit higher yet, and on the next bin we're back up here kind of into sort of a mid-range like that. Okay, so far so good. So positive peak, negative peak sample. There's also a mode which is called, and I'm running out of colors, there's also a mode called normal. Normal detection means that the analyzer runs positive peak on one bin, negative peak on the next bin, then positive peak, negative peak, then positive peak, negative peak, and so forth, alternating. So in so-called normal detection, we would run positive peak, then we would run negative peak, positive peak, negative peak, and so forth across. And so forth across. So then what we would plot on this spectrum analyzer display would be something that would look like that, then like that, then back up here, then down here, then up here, and so forth. Whoop. Then back up here, okay, and so forth across. Usually, when most spectrum analyzers turn on, initially, they're running in so-called normal detection, and so the result of that is that you see a level here on one bin, then a level here, then a level here, then a level here, and so forth. And so when you first turn on the spectrum analyzer, you get that really wide band of color running across the display. That's just because we're going positive, negative across in the so-called normal mode. One thing that's a little bit handy about normal mode is if you look at noise, you'll see a band here that's 20 dB wide or wider, whereas if you're looking at something that is some sort of a continuous wave signal, then the positive peak and negative peak will pull up together and the band will disappear. So this gives you a little bit of a clue as to what the duty cycle of the signal is. Duty cycle being the percentage of time that the signal's on divided by the total interval of some part of the waveform. So that can be something useful about normal. With that said, I've never used normal much. Now, what if you want to know the average power in the waveform? This is where it gets a little trickier, because the ideal way to get true linear average power in a waveform is to obtain this value where power average would be equal to the root mean square of the values in these of the waveform in these bins, like so. It would be 1 over n times the summation from I equals 1 to n of x sub I squared, where this would be x1, x2, x3, x4, etc., right on through like this, until finally at the end of the bin we would hit x sub n. So if you imagine breaking this waveform up into n samples, each called x, and then summing up the squares of those samples, dividing by n, the number of samples taking the square root, that would be a root mean square power measurement. To my knowledge, this has never been feasible to implement strictly with an analog spectrum analyzer. It's relatively easy, however, to implement with a digital spectrum analyzer. However, with that said, there are some ways to look at average power with an analog spectrum analyzer. But in any event, the key thing to remember here is that we could either get root mean square power, or there is an alternative, and the alternative is to get the average decibel power. Now, to get the average decibel power, I'll go back here. To get the average decibel power, with an analog spectrum analyzer, which is what we're going to get, the key is to set the video filter to a value, set the video bandwidth to a value that is substantially less than the bandwidth of the IF filter up here, the resolution bandwidth. So, for example, if we were measuring power in a 1 megahertz bandwidth at the IF here, then the video filter could be set to a value of, say, 1 kilohertz, 1,000th. Say 1,000th of the value of the IF filter, and this low pass video filtering has the effect of smoothing the waveform and giving us something which is a decibel average. It's not a linear power average. The reason it's a decibel average is, remember that what's coming through that filter has already been logged. So we'll look at it with this spectrum analyzer, because this is a digital analyzer where we can implement either detection algorithm. We can either look at average decibels or actual RMS linear average power. So any questions up to that point about how this is going to work? So what I'd like to do next is, first of all, look at the spectrum analyzer noise with positive peak, negative peak, sample, and RMS power, and the decibel average power. And then we'll turn on a microwave oven and we'll look at its waveform. We'll use the microwave oven because it puts out a nice pulsed waveform.
Now, Frank, one point,
Yeah.
when you write your equation there, the P average, upper left-hand corner, you're assuming those X sub i's are power readings, is that correct?
Yeah, where
Okay.
these are, good point, where these are power,
in watts.
linear power, right?
Okay.
Where these are linear power. Now, as I said, with a digital machine, it's possible to do that. With an analog machine, that becomes a difficulty.
Now, if you were
But yeah.
viewing your signals in terms of voltages or electric fields, whatever quantities there, you would not want to have that square root term.
Then you wouldn't, right? Correct. Good point. Good point, Bob. Yep. Exactly. Yep. Okay. Okay.
Rock
So.
concerts as well.
Yeah, great for rock concerts. These are also good for star parties. You can see the beam going up in the sky. You can point the constellations out to people, star to star. You can actually see the beam going up.
That sounds pretty cool.
Oh yeah. So here's the spectrum analyzer. Now, remember when we were talking last time, I always go through this sort of mental setup routine. First, I adjust dynamic range. So amplitude, attenuation, I'm going to set that over here to 0 dB. I'm going to let my eyes adjust slightly to the darkness, okay? And now, this is in so-called normal detection right now. I'll prove it by going to the detector button. So here's detector, and it's set to automatic, which is normal. So here we get positive peak, negative peak going across. We have 601 bins set up right now, which is fine. Now in this spectrum analyzer, we can actually change the number of bins if we so desire. We can set the points. They call them points. I call them bins. To, for example, 1,001 points, and then enter. That just makes the density look higher on the screen. That's all. As I said, if you had a carrier wave in here, you'd see these pull up into a single thin line and then go back down, because the negative peak and positive peak on a carrier wave are going to have the same value. Now, let's pick a frequency. We'll say we're going to sweep across a frequency range that's going to start at 2400 megahertz, and we'll go to 2600 megahertz. This is a spectrum band which is reserved for industrial, scientific, and medical devices, including microwave ovens, cordless phones, local area networks that are wireless, that kind of thing. It's kind of a catch-all spectrum band. And we'll set the bandwidth. This is our convolution function. We'll set the bandwidth, resolution bandwidth, to equal 1 megahertz. And that low-pass filter is set to be equal to the video bandwidth, so the video filter is in effect not affecting our waveform, because as long as the video filter is as wide or wider than that resolution bandwidth, then it's having little or no effect on the waveform that we're seeing. And there's nothing hooked up to the spectrum analyzer right now, so what we're seeing here is in fact noise. And in fact, I'll bring the reference level. I'm just changing the reference level at the top here, just so we can see the noise more clearly, not at the bottom of the screen. By the way, this noise has this is thermal noise, so this has a kind of a fractal characteristic in time, in that this is a sweep time of 1 millisecond. If I make the sweep time on the noise 100 milliseconds, whoops, sweep time manual. Sweep time 100 milliseconds. It has the same sorts of characteristics. Sweep time 1 second, to look like that. This again is a positive peak and negative peak. Now there is something that is going on here. Because I slowed the sweep time down, I've got more time per bin, and the reason I set this to 1,001 bins was to make the math simple. With a sweep time of 1 second and 1,000 bins, I now have 1 millisecond per bin to get a positive peak level, and I have 1 millisecond per bin to get a negative peak level, and so I have a better chance of hitting, if you will, a sort of a full peak level here for this bandwidth on the noise, and hitting a pretty low negative peak value over here on the noise. I'll show this a little more clearly by going to detection, peak. We'll just pick off positive peak. All right. So here what's happening is we're sweeping in 1 second across the display over and over and over again. And we have 1,000 bins, 1,000 points, so we know that we are spending 1 millisecond per bin. And in each of those 1 millisecond intervals, this analyzer is picking off the highest power value that occurred in that millisecond and is plotting that value. So we will go to, I'll go back to sweep time here, go back to say, 20 milliseconds. Like that. We get a little different characteristic at 20 milliseconds. We'll get a little different characteristic at 1 millisecond, just because we're spending less time per bin. In fact, at 1 millisecond with 1,000 bins, we're only spending 1 microsecond, 1,000th millisecond. So now we're spending 1 microsecond per bin picking off a peak value. But I'm going to go back to to show how the detector works differently on the noise, I'm going to go back to a sweep time of 1 second. All right, so there's positive peak, 1 second. That's 1 millisecond per bin. Now we'll go to, trying to see in the dark here, so-called negative peak, where it picks off the lowest value from the analog to digital converter in each of these bin intervals of 1 millisecond each. And that's down there. In fact, here I'll do this. We'll save that trace. And then, peek down here. Okay. And then, trace. There we go. Okay, so that's the positive peak level up there. That's the negative peak level down there. I just saved those traces. The difference between these levels and this analyzer is about 10, 20, 35 to 45 dB difference, give or take. So say a 40 dB range there. Notice that there's a kind of a maximum value that the peak detector can hit on noise that to some extent is limited, in fact it's entirely limited, by the bandwidth in which we're operating within the bin cycles. Down here, on the other hand, we're seeing the effect of noise being able to go to an arbitrarily low value and taking a log of that. So we could, in principle, hit minus infinity. What we're probably hitting here is the bottom of the analog to digital converter system on these low points right in here. But negative peak can drop way down when you're looking at it in decibels. And in fact, eventually you'll just hit the point where, in effect, the ADC has hit zeros all the way across. The actual value could be lower than that, but once you've hit zeros all the way across, you're done. Now we'll go to a third trace, which will be sample, and we'll go to trace 3, clear right. Okay, now this is sample. Sample, remember, is pulling off a random value, in effect a random value, which just depends on what the waveform is doing at the randomly selected moment in time when the ADC is pulled for a value. And so the values on this trace can run almost, in fact sometimes will, right there, it hit the positive peak level. Keep looking here. There, it hit the positive peak level right there and so forth. And every so often, you'll also see it hit as low as the lower negative peak values. There, that one comes close anyway.
Can you set that? Can you set whether you pick off the first?
Not,
or the last point, or-
yeah, the question is, can you set which one you pick off? Not to my knowledge, or at least not with this model of analyzer. Now, there might be some analyzer somewhere where you can do that. And of course, you would have to be cautious with a sample detector that there's a chance that you could wind up sampling in some way that's synchronous with the waveform that's coming into the spectrum analyzer. In which case, it's not random anymore. But this is the so-called sample mode. So now we see positive peak, negative peak, sample. Now there are some waveforms where sample would look the same, for example, as positive peak. If we're looking at a carrier wave, like we did last week, where we just have a sine wave at RF being put into the spectrum analyzer, then the input signal always has the same power level no matter when you look at it, and the positive peak's going to look the same as the sample. We do see a lot of difference, of course, when we're looking at thermal noise, and we'll see how this also behaves with the microwave oven shortly here. Now, the next one that we'll pick off will be, now let's look at averaging. This spectrum analyzer, because it's digital, allows us to look at either the RMS average or a log average, or for that matter, a voltage average. I'm not really going to talk about voltage average except to mention that it's there. If somebody wants to look at that in more detail, they can certainly do that. Right now, let's look at the root mean square average, the RMS. So we have to pick that, which is under, and this is a little counterintuitive, a separate submenu. We pick power, and in fact it's already set to that, but I'll go ahead and set it anyway. Here we could go log power average, linear power average, which they just call power average, RMS or voltage average. And in fact, we do have that selected right now. Okay, so now let's go to trace, and let's get rid of the negative peak. I don't really care one way or the other. No, actually, we'll keep the negative peak. No, yeah, we'll get rid of the negative peak here. So that was trace number 2. We'll go clear right on it. Okay, so now the cyan line running through here is the RMS average. And that is doing the computation in which it takes the square root of 1 over n times the sum of the squares of individual power values. Now, in order for RMS to work well, you should have a statistically large number of samples in the computation. And as long as we're running at a slow sweep time like we've been running, which is 1 second, we can do that. But now I'm going to go to a shorter and shorter sweep times. Watch what happens with the cyan trace as I go to shorter and shorter sweep times. Here's 1 second. There's 750 milliseconds, 500, 300, so forth on down. 75, 50, 30, 20 milliseconds. Go down to 1 millisecond. Okay, and look what's happening as I go down to 1 millisecond on the sweep time, which means I'm spending 1 microsecond per bin. The RMS trace looks in effect identical to the old sample trace that I saved. And the reason is that apparently I'm getting about one sample per RMS average, in which case I'm not averaging anything. Well, I'm mathematically averaging it, but I'm averaging something on itself. So
An
in
average of
effect,
one.
I've got an average of one, right? So as I said in an earlier talk, if I'm averaging your height. If I want to get the average height in the room and I only use your height as my only sample, then your height is the average. So this has come up before. People have said that they want to run some kind of RMS average and they want to do it really fast, and they do that, and then they say, well, that looks the same as this other as a sample. I would say that's right. That's because you weren't really getting any averaging null. But it's averaging. No, it's running an averaging function, but on a sample of one. And so we can also tell here on an empirical basis that apparently we get about one sample per microsecond effectively on this machine, because when we get the sample time per bin down to about 1 microsecond, we can't tell the difference between the so-called RMS average and the sample mode. Now I'm going to go back to slower and slower sweep times, and again you can watch what happens to the RMS average. And in fact, I will, just to make this a little easier to follow, I will kill trace 3, okay, and just let you see that a little more clearly. Whoop. There we go, sweep time. So again, slow sweep times, not much averaging going on. Let the sweep time creep up. And of course someone could say, well, how long do you need to sweep? And I would say, well, it depends upon how good you want the RMS average to be. Here we're getting a spread of maybe a dB back and forth on the RMS power in the thermal noise. 3 seconds, okay. At this point it's gotten so tight that we're probably well within the uncertainty of the spectrum analyzer itself. So let's save that trace as a view on the screen here. All right, whoop, as a view, sorry. Trace 2 view. All right. Okay, so we'll just save that one in place. So remember that that's the RMS. Now let's go to trace 1, which was the positive peak. We'll let it clear right. And now we'll go back to the averaging mode. And let's go to the decibel average, which is the log power average here. We'll select that. And what we see is that when we average decibels as opposed to averaging linear power values, there's the average decibel power value is about 2 dB less than the linear power value for thermal noise. So I'm not going to say that's good or bad, but that's just how the math works. So leave it at that. Okay, trace. We'll view that. Now, having gotten those 2 traces, let's do the following. We'll bring up a third trace, we'll run clear right. Now we'll operate this analyzer as if it were an analog spectrum analyzer where we don't have an RMS algorithm built in. And in that case, what I will do is, in fact, set the detection mode to sample. Okay, so now it's just pulling off the random thermal energy points on a bin-by-bin basis. And now we will go to the bandwidth settings, and we have a 1 megahertz resolution bandwidth. Now we're going to manually select that low-pass filter, and we're going to start making it more and more narrow compared to the resolution bandwidth. So there it is at 300 kilohertz. There it is at 100 kilohertz. There it is at 30 kilohertz, 10 kilohertz, 3 kilohertz, 1 kilohertz. I recommend going to about 1,000th of the value of the resolution bandwidth. And guess what? It's smoothing the waveform, but because it's operating after the logging section in the spectrum analyzer, the value that we get there is not the linear power average, it's the decibel power average, which is what it is.
So you're just taking a low-pass filter and basically just squeezing
Right.
it down and then
Right.
intercept, just picking off the DC component.
And just picking off what amounts to the DC component. Exactly. Exactly. That's exactly right. And then we'll save that as a trace. Okay. But we see that the 2 are identical. Now there's yet another averaging mode that we can go to. And this is an averaging mode in which we gotta find this. Oh yeah, bandwidth. Okay. Okay. There is yet another averaging mode that we can go to. Oh, back up. I'm going to bring the video bandwidth now back up to 1 megahertz, okay, like so. And remember that the detection algorithm that I'm running is still sample here. And I'm going to go ahead and let this trace overwrite itself, because I've kind of run out of traces, and we've still got the two basic traces. Cyan is the linear power. Yellow is the average decibel power. We're back to 1 megahertz bandwidth on everything, running in sample mode, and now we'll go to a mode where we have. Find the right button. Sorry. Now we'll go to trace averaging. Trace averaging is a screen function which is normally available on both digital and analog spectrum analyzers. In screen averaging, we actually run a trace across here, and it remembers all the bin values across the trace, and then on the second trace, it averages the decibels on the second with the decibels on the first, and on the third trace, it puts those values into the average, and so it keeps a running average until it's averaged the bin values on 100 traces on a bin-by-bin basis. In other words, if you want to pick off this bin, right here at this point on the spectrum analyzer screen, and we have that set to 100, it will take 100 samples on that bin on 100 successive sweeps, and it will average them, but what it will be averaging will be the displayed values on the screen, and those are decibel values. So let's go ahead and do that. We'll turn on the averaging, and we'll watch it actually kind of converge here. See, it's already starting to converge down. That's the second, that's the third. You can keep track on the counter over here. There's number 4. And I won't put you through the agony of going through 100 at this speed. Let's go ahead and speed up the sweep time a little bit. Whoop. Speed up the sweep time a little bit. There we go. Watch it. There's 40, 50, 60, 70, 80, 90, 100, and it stopped. And there we go. So that converges again down to the decibel. So the only way that we've seen so far to get a linear power average on the spectrum analyzer is in fact to have a digital machine that in fact can do the RMS computation. Otherwise, you're typically going to be getting decibel averages, whether you use low-pass video filtering or use trace averaging. You're going to get the decibel average instead of the linear power average. Now, sometimes that doesn't matter. There's a calibration technique that we use with noise diodes, which I'll talk about in a later discussion, where we only need to know the difference between two average power values, in which case it's fine to use, as it turns out, use the decibel average here, but just something to be aware of. All right, now, there's one last thing that I want to point out, and this involves going back to the positive peak. We'll go back to trace 1, clear right. Trace 2 will blank it. Trace 3 is already blanked. All right, so far so good. We'll go to the trace averaging here, and we're going to turn that off, get rid of that now. Okay, so that's off. Now we're going to go to peak detection. Go back to positive peak detection here. All right, now we're back to positive peak. And this is a mode called maximum hold mode. This is often confused with positive peak, and I mean, they sound similar. Max hold, positive peak, what's the difference? Okay, positive peak detection, as we've now seen, is the process of latching to the highest power value that occurs in each bin within whatever the sampling interval is for that bin. Maximum hold mode is a trace mode. In maximum hold mode, the machine remembers the highest level that has hit any given bin since you actually hit the max hold button. So I'm going to hit a max hold button right now, and you're going to see this start to come up. And then I'm going to bring up a second trace that shows you what's happening in real time. This trace shows, the cyan trace shows what's happening in real time with the peak detector. The yellow trace shows the memory of what has happened since I hit the max hold button on a bin-by-bin basis. Now, you could run maximum hold trace mode with positive peak detection, like I'm doing here, But you can also run max hold mode with other detector algorithms. For example, let's go to sample. We'll run the sample mode with maximum hold on the trace. Go back to trace 1. I'm going to do a clear right on trace 1. Now I'm going to do max hold. Okay, and now we have a memory of the highest level that the sample detector has hit so far. Now if we wait long enough, eventually that memory of what the sample detector's seen will eventually look the same as what the positive peak saw, but it's going to take a while to get there. And I won't subject you to that. So maximum hold mode does not mean positive peak. You can run maximum hold, which is a trace mode, which remembers the highest level that you had on the analyzer on any given bin since you hit the button, in combination with whatever detection algorithm you feel like you want to run. Here's one that you wouldn't think you'd normally want to use, for example, but you can do it. We'll go to negative peak detection down here, and then we'll go back to max hold on trace 1. So now we're seeing the maximum level that the negative peak detector is hitting. I've never had to do this in any actual application, but if you wanted to, you could. It'll allow you to do it. So again, I just want to reinforce the idea that maximum hold mode is a trace function. But oftentimes if you're talking to someone who wants a measurement done, they'll say, I want to see that in max hold. Well, what they mean is they want you to use positive peak detection. So you may have to get that clarified if you're talking to someone. Now, do you really mean max hold, or do you really mean positive peak, or not? And you could run maximum hold mode with RMS detection, although again that would be really nuts because the RMS is going to converge down to a single value, so why run max hold on that? You can also run, as we see here, a minimum hold, in which case you go down like that. Now with negative peak detection, minimum hold might make more sense because now you're remembering the lowest value that that minimum detection algorithm has seen since you hit this. And if we wait long enough, this will eventually kind of bottom out along here because, as I said, what's happening when we go to extremely low power values on thermal noise is that we're taking logs of numbers that are going to approach negative infinity, and of course what really happens in the machine is we're going to hit all zeros on the ADC converter. So we're simply going to run out of dynamic range down here on the ADC, but that's the basic idea. So much for thermal noise. Now, who's ready for well, first of all, ask if there are any questions. Second of all, okay, we'll go back to this. Second of all, is everybody ready for the microwave oven?
Absolutely. We're waiting with bated breath.
We're waiting with bated breath.
Oh,
Ow! Oh, God. Okay. Let me raise the screen momentarily. First, I'll give you a very brief introduction to what the microwave oven is actually doing. Yeah, thanks, Teresa. First of all, what is a microwave oven? A microwave oven is actually a microwave power production unit that takes line power at 60 cycles or 50 cycles if you're in Europe in to one end of a tube called the Magnetron and spews microwave energy out this end. The Magnetron was the invention that arguably was key to the Allies winning the Second World War because it's a miracle. You can plug it into a generator on this side and you can get microwaves out this side, and these microwaves can come out in extremely high power pulses. This is key because when you're building a radar system you need to hit very, very high peak powers so that the echoes coming back from distant targets are still strong enough to detect in your receiver. And you would like the radiation wavelength to be relatively small, about this big, so that you can focus the energy tightly in space with antennas that are only about this big. And in order to get wavelengths this big, you're automatically at microwave frequencies. And this invention was not obvious. And it was in fact developed originally by some British physicists during the Second World War. They knew that they had a way to generate the microwaves. They didn't have a way to produce these magnetrons in large numbers. They carried the first prototype magnetron, to my knowledge, across the Atlantic on a ship. They showed this off at the MIT Lincoln lab, and the people there basically said, oh, that's how you do it. And then the United States' industrial manufacturing capacity was able to make tens of thousands of these things and put microwave radars in aircraft. They put them in ground units, they put them on ships, and it was just simply key to winning the war. And now it heats your frozen burrito. the way that the magnetron works, just very, very, very briefly, is to orbit a current inside a cavity with a magnetic field running at a right angle to the cavity. Schematically, it looks a lot like a cyclotron, which is a particle accelerator that particle physicists use. The beauty of this is that these accelerated charges, they're being accelerated because they're moving in a circle, the accelerated charges radiate RF energy. And that RF energy is tapped inside that little cylindrical unit that you see in there, and that energy that's tapped out of that unit gets spewed out of this end of the magnetron. These fins are just for heat dissipation, the fins around it. The power supply it's hooked up to is on the order of 10 to 20 kilovolts is the potential it generates. The current's not terribly high, but the voltage is high. If you're ever working on a microwave oven, you need to touch across the contacts and short it before you do anything else so you don't blow yourself up. That said, this would make a great ray gun. You could put the power supply on your back, and you could carry this thing and you could pull the trigger and it would squirt microwaves out as you're walking around. It'd be so cool.
Originally, Frank,
Just a
radar
thought.
was conceived as a death ray, and then they
Yeah,
discovered,
yeah.
you know,
And then they discovered there are other applications.
Right.
You could detect things at a distance.
It's actually part of
Yeah,
a spell.
and you could cook burritos. In fact, and by the way, this is non-ionizing radiation. So the power level on a photon per photon basis is too low to break molecular bonds directly, but the RF radiation does vibrate the water molecules back and forth, and that heats the water molecules in either a burrito or in you if you're exposed to this directly. And again, the story goes that guys who were standing guard around radars in the Second World War realized that they could get warmer if they stood over in front of the radar. Oh, much better here. And it might not even hurt you. I don't know. I really don't.
Stuff,
But,
baby bump.
yeah. In a microwave oven, this thing is mounted. In a microwave oven, this tube is mounted like this, with the business end pointed up, and there is a waveguide inside that channels this energy around and then down into the cooking cavity in the oven over here. So this is sitting like this in the oven, channels it around, goes down to the cooking cavity, and cooks the food. This thing is not stable in frequency. The frequency that it generates is centered at about 2,460 megahertz, 2460. It operates in the 2400 to 2600 megahertz frequency band. 2560. 2425. I'm saying something wrong here. We'll see. We'll take a look at the spectrum analyzer. Actually, I think I got a number wrong here, but this does not radiate on a stable single frequency, and we'll see that effect. The argument that's used for this is that this prevents hot spots from building up in the cooking cavity, because you don't get normal modes in here where you get a lot of radiation in one place and very little radiation in another place. Over time, the effect averages out inside the cavity. It also allows the magnetrons to be built cheaply, because they can be built to a fairly low spec in terms of being frequency stable. So much for that. Oh, and this thing pulses 60 times a second, and it runs at about a 50% duty cycle. So the pulses come out for a length of time, and then the pulses are off, and then on, and then off. And the pulse length when it's on is equal to the amount of time that is off. So it runs at a so-called 50% duty cycle, and when we look at these pulse shapes with the spectrum analyzer in the time domain, we won't see the RF oscillations, but we will see the envelope of the pulses running at this 50% duty cycle, where the interval between the pulses themselves here is 1/60th of a second. So, and that's not an accident. It's just synchronized to line power. It just makes it easy to build it. So, in order to see the energy, we'll use a cavity-backed spiral antenna. This is an antenna design which is very compact. It's very broadband. This particular antenna runs from 1 to 12 gigahertz. It consists of a wire on a surface here, and the wire has the shape of an Archimedes spiral. It's very, very tightly wound in here, and the spacing between successive turns of the spiral gets wider as we go out toward the edge. So it's a spiral, and it's in front of a microwave cavity, so it's a cavity-backed spiral antenna. I will do one other quick digression on that. These antennas, this type of antenna is extremely useful for us when doing radio measurements because it has a beam width at the 3 dB points of the antenna, which is about 90 degrees wide. It's about that wide at the 3 dB points. So it's not terribly directed, but it's got a little bit of directivity. You can use a set of either 4 or 6 of these antennas to do direction finding on radar signals. And we'll talk about that at a later date also. You set up a set of either 4 of these, 1, 2, 3, 4 like this, or a set of 6 of them in a hexagonal pattern. You can direction find on radars with these. These were not manufactured for the purpose of doing radio measurements. The actual function for these things usually is in electronic warfare, in which you've got some kind of an airplane shape like this that you're flying with a tail on it back here. And they'll actually mount one antenna here and one antenna here and one antenna back here on the tail, another antenna back here. And because each of these antennas provides about a 90-degree beam width, like so, around the aircraft, a set of 4 of these gives 360-degree coverage around an aircraft, and run with a receiver, these can be used to alert a pilot that he's being targeted by a radar, because he's got nice 360-degree coverage all the way around the aircraft. And again, if you do it right, you can actually tell what direction the signal's coming from. These are also deployed on ships for the same purpose. So, with that said, we'll hook this up here on the table. And I'm not even going to point it at the microwave oven. I'm just going to put it in here like that. It'll be close enough for what we're going to do. Okay, now I'll turn on the oven. Now, the oven is running and we're seeing pulses coming out of the oven. Oh, we're going to kill this. There's a LAN running in here. I don't want that on because it's in the same band. Okay. Now, we are going to look at this with positive peak detection, like so, and I'm going to bring the reference level up, like that, and now we'll go to maximum hold trace mode, and we'll watch the microwave oven spectrum form itself up. Close that door. Okay, so what we're seeing here is the memory of the highest level that we've been hitting with the microwave oven pulses versus what we're seeing moment to moment on a sweep-to-sweep basis across here. And we see that this thing's actually running between 2400 to about 2500 megahertz. So let's look at that in a little more detail. Trace frequency, stop frequency 2500 megahertz. Okay, like so. All right, this is a typical microwave oven emission spectrum, and at the moment we're running without the preamplifier turned on. If I do turn on the preamplifier over here, that's that internal preamp that's at the RF front end. This will give us more sensitivity. It'll lower our noise floor, and see we're actually saturating our display up here. Which we don't need to do, so I'll actually turn off the preamp, but for our purposes. Amplitude, reference level. There we go. So back down to this. So here we see the this spectrum of this pulse source putting out 60 pulses per second, and people will sometimes look at something like this and they'll say, "Oh, it's frequency hopping." Or, well, it's not really frequency hopping. It's just kind of frequency unstable in this particular case. We can bring up a marker mode and come across here. The maximum power out of this thing is up here at about 2460. Did I say that right earlier? I thought I said. Did I? Okay. So it is 2460, where this thing comes up and hits max power right in here. Now this is using, since we're talking about detection modes, this is using positive peak detection. Now we'll go to sample detection. In sample detection, we do sometimes hit the same levels as we did with positive peak, but a lot of the time we don't, and that's because this thing's, the spectrum analyzer is just pulling off these basically random points. We can also go to, and in fact I'll do this, we can also go to averaging. I just set it to RMS power averaging. And now, in this trace mode, we'll go to, okay, we'll let it RMS power average. And because this oven is running at a, that seems a little too high power. And go back to detection. Ah, sorry. Okay. RMS. Okay, now. Trace 1. Okay, sorry. There's the RMS, which is virtually the same as the peak. It's a little closer than I thought it would be. Oh, I know why. Oh, and here's, okay. And the reason that this RMS right now is hitting almost as high as the peak is because the sweep time is really fast. So again, we're not seeing much averaging. Let's make the sweep time a little slower. All right. And now go back to trace 1, clear right. Okay. And now maximum hold. Now we're max holding with RMS, and we're sweeping slowly enough that we get a nice number of samples. So we're really getting an average. See, that's the kind of, I was going to demonstrate that, and even I got caught by the pitfall right now. I was sweeping so fast that I wasn't really averaging much with my averaging algorithm. Now we'll average with the averaging algorithm. It takes a little longer, obviously, but in fact, I will speed the sweep time up just a little bit. We can afford that much. Okay. There we go. And now we see that right here in this frequency range, the average is almost the same as the peak, but down in here, the average actually departs some from the peak. There's actually a reason for that. The oven spends most of its time, as it turns out, the oven's spending most of its time on frequencies that are right up in here. It does not spend much of its time at these frequencies, and it doesn't spend as much of its time down at these frequencies. It's just the way the magnetron happens to behave itself. So there's the RMS. Gradually filling itself in. Oftentimes with pulsed emitters, you're not that interested in getting RMS on a pulsed emitter. Oftentimes with pulsed emitters, the real interest is getting the maximum power with a peak detector. Certainly when we eventually get into radars, that'll be the main goal. But this does show the difference between RMS and peak for this sort of a pulsed emitter. Now, having done that, let's do something kind of interesting. Well, first of all, any questions on that so far? Just wanted to. Okay, so we've gone through the different detection algorithms on thermal noise, different detection algorithms on a pulsed microwave oven emitter. Now let's go to this frequency of 2460. This is a kind of an extra thing I thought I'd throw in. Center frequency, right here, 2460 megahertz. Okay, and now we'll go to a span. That's the frequency range across on the spectrum analyzer. A span of 0 hertz. So we'll now look at this thing in time. Okay, and then we'll go clear right on trace 1, we'll blank trace 2, we'll set our detection algorithm. So here we're seeing a combination of the microwave ovens pulsing on and off 60 times a second, and this thing is in fact sweeping 1 sweep per second, so we're seeing 60 pulses across here, combined with the fact that it's tuning on and off of 2460 megahertz. And if we want to see this for a larger amount of time as it sweeps back and forth, we can increase our resolution bandwidth so that we're looking at a window 8 megahertz wide, let's say, instead of looking through a window that's 1 megahertz wide. So there's now we're looking through a window that's 8 megahertz wide. So anytime that the microwave oven's fundamental frequency, that is the frequency of the magnetron, is somewhere within plus and minus 4 megahertz of our tuned frequency, we're seeing it running back and forth through here. Conversely, if we make the resolution bandwidth here less, there's 3 megahertz, there's 1 megahertz, there's 300 kilohertz, 100 kilohertz, 10 kilohertz, like that. I'll come back up here. There we go. There. 30 kilohertz. Now we're looking through this tiny little narrow window. We just don't see the oven as much of the time because most of the time it's outside our little 30 kilohertz window. So now I'm going to come back up here to the 1 megahertz. Oh yeah, okay, let's do 1 megahertz. Well, 3 megahertz. Okay, that's fine. Doesn't really matter. Now let's look at this on more of a pulse-to-pulse basis. This is what I like to do with any pulse emitter if I'm looking at it. Go to the sweep time, bring the sweep time down. Here's sweep time. I'm going to come down to where I can, that's not bad right there. Okay, now I'm going to go to a sweep mode where instead of running continuous sweeps across like this, I'm going to go single. Now in single mode, the way it works is there's actually a single button here, and I can take a sweep by pushing my button with my finger. So I'm just taking individual sweeps here like this. Ah, that's a nice sequence right there. So this is a set of microwave oven pulses. And what we see here is a pulse when the microwave oven is tuned basically right on our frequency 2460 in our bandwidth of 3 megahertz. Here the oven's tuned on frequency. Here I can tell just by looking at the pulse shape that it's tuning off our frequency. The reason I can tell is that's an effect called a Rabiers effect. And here the oven is tuned so far off that I'm actually, well, here. This is the pulse width, the distance between my fingers. Here's the pulse width translated to the cross. We get this Rabiers effect. Here's the pulse width from that little spike to that little spike, and we don't even see any energy there or there, but we see some in the center here. Here the oven is still tuned somewhat off frequency, and here on the last pulse in this little sequence I just recorded, the oven's basically tuned back on frequency again. And I can look at these pulse shapes and immediately tell by the pulse shapes what's going on. People say, what do you mean? I mean, don't you need a vector signal analyzer with the ability to show frequency and function time? Well, yeah, that is nice to have because then I could really see more how this varies with time. But I'll wrap up today by just explaining how you can look at something like this. And when you see this Rabiers effect, you'll know that you're looking at a pulse signal that is not tuned to the same frequency as you're measuring. And like I said, that's what I'll wrap up with. Just kind of a little extra. Yeah, thanks, Teresa. Here's what's going on. This is kind of a prelude to measuring radars. Okay. Just erase this stuff right here. It's all about convolution bandwidth. The effect is as follows. If we're running a pulsed transmitter and we're looking at that transmitter's spectrum envelope, I'm just going to draw the envelope of the pulse transmitter spectrum. I'm going to draw it to look like a sin x over x squared spectrum like this, where this spacing is equal to 1 over the pulse width, and this spacing is equal to 2 over the pulse width. And assuming that we're putting out a pulse sequence in time that looks like this, just a nice set of pulses in time, where this is the pulse width, call it tau, like so. So this is equal to 1 over tau. And this is equal to 2 over tau. If we examine the spectrum with a convolution bandwidth, which is about as wide or a little wider than the central lobe in the spectrum, and we have it tuned onto the central lobe in the spectrum, the effect of convolving the energy in this part of the spectrum, which is in fact itself a set of emission lines, will be to show us a picture in the time domain, which we were just looking at with the spectrum analyzer. This throws people because it's a spectrum analyzer, but we can just go to 0 Hertz span and we see what's happening in time. It's like a really slow motion oscilloscope with a detector built in. In the time domain, the effect of looking at the energy in the lines in the pulsed emission spectrum in the center lobe of the spectrum, where this is our convolution bandwidth, which a moment ago we just set to 3 megahertz. I just picked that as an arbitrary number. We'll see a set of pulses on the spectrum analyzer, which will in fact have shapes that will look basically like that, basically the same as what we're putting in, where this is the envelope of the pulse shapes. This is what's going in, that's what we see coming out. But, here's what happens if our convolution bandwidth is not tuned to the same frequency as the center of the spectrum. If our convolution bandwidth is tuned over here, and we're convolving this subset of lines, over here, what we see instead in the time domain is a picture that will look like that. We'll see the, well, it won't have a higher amplitude, they'll have a lower amplitude there. All right, like so. We'll see the same width on the pulses as we saw before, but the effect of not convolving the lines in the center part of the spectrum is to give us a time domain detected envelope, which actually will look ragged and noise-like. And you can actually go, I've actually done this with the Fourier transform on a computer, where I actually slide this bandwidth window back and forth, and just for fun, I look to see what the effect is of convolving different subsets of spectrum lines out here. And in fact, you get all sorts of interesting little pulse shapes. So when I saw that thing go down into the rabbit ears, and then I saw it look like 2 little spikes, and then I saw it come back up to looking like a well-formed pulse, I knew immediately that what's happening is that this part of the spectrum in here is moving back and forth relative to my filter. And since I was holding my filter on a single frequency, which was 2460, I knew that the oven itself is sliding back and forth in frequency, and I actually saw that in that set of pulses. So that's all it is. But if you're ever looking at a pulse, but conversely, if you're ever looking at a pulsed emitter and you see a time waveform that looks kind of like that, and then later on you see a time waveform that has the same width and looks like that, you know that you're looking at the pulsed emitter with a bandwidth in your measurement system, a convolution bandwidth in your measurement system that's not tuned to its fundamental frequency. It's off tuned somewhere. You can actually see it slide back and forth through there. So, just an interesting thing to know. Any questions? Okay, well that's all I had for today. Mainly I just want to talk about detection algorithms. So, is everybody clear on how the detection algorithms work? Positive peak, negative peak sample, linear average, decibel average, and you can get decibel average by doing trace averaging, and you can get it by doing low-pass video filtering, and digital machines will typically allow you to do RMS, and analog machines will probably, as to my knowledge, will never give you that. To my knowledge, I hate to be proven wrong on that, but yeah, so. Okay, that's all I've got.